Hi, this is part 2 of 5.2. We're talking about polynomial functions. So let n be a non-negative integer. A polynomial function is a function that can be written in the form below. This is called the general form of a polynomial function. Each ai, so each a, which would represent the coefficient of x, is a coefficient and can be any real number, but a of n cannot, or an cannot equal 0. Each expression aixi is a term of the polynomial function. So we often rearrange polynomials so that the powers are in descending order. So we call those powers, we call them degree. So whatever that highest power is, that is the degree of the polynomial. So if the highest degree is 2, like for a quadratic, that would be the degree of 2. If we had a cube, the degree would be 3. Whatever the highest one is. Now, whichever term that the highest degree is in, we call that the leading term, whether it is here in the front or whether it's anywhere else. And then the coefficient in front of that leading term, that is considered the leading coefficient. And so often we rearrange it so that the powers go in order of degree from highest to lowest, so that you can easily see what the leading term is and thereby see the degree of the polynomial and the leading coefficient. So how to, given a polynomial function, identify the degree and leading coefficient? First, you find the highest power of x to determine the degree of the function, and then you identify the term containing the highest power of x to find the leading term, and then from there you identify the coefficient of the leading term. So in this example, we want to identify the degree, the leading term, and the leading coefficient of each of the following polynomial functions. So I'm going to make a little table, and I'm going to put the leading term, and then we need the leading coefficient, and then we need the degree. And fill that in for each of these. So what helps is if we first put these expressions in order, or these functions in order from highest degree to lowest. So this first one would be f of x equals negative 5x to the third, because 3 is the highest exponent, plus x squared, because 2 would be the next highest exponent, and then plus 4. For g of t, actually that one looks like it's already in the correct format, because it goes 6, 2, and then 1 for exponents, so that's already in order. The last one, h of p, looks like we'd have negative 4p to the third plus 3p plus 5. Okay, so first, and it looks like I ran out of space there, so let me rather quickly kind of write that underneath here. So we have negative 4p to the third plus 3p minus 5. Okay, so for the first one, the leading coefficient, or the leading term, is the term that has the highest exponent, the highest degree. So that would be negative 5x to the third. The coefficient would be negative 5, and the degree would be 3. For the second one, we have 6t to the sixth. That is our leading term. Oops, 6 right there, sorry. And then the leading coefficient is 6. The degree is also 6. And last, our leading term is negative 4p to the third. Our leading coefficient is negative 4. Our exponent, or our degree, is 3. Okay? So you guys pause the video, try this one, try to identify the degree, the leading term, and the leading coefficient of f of x equals 4x squared minus 6x plus 2x minus 6. Okay, so first I'm going to rearrange it, and I have negative x to the 6th plus 4x squared plus 2x minus 6. Here's our leading term. So our leading term is negative x to the 6th. Our leading coefficient is the number in front of x to the 6th, which would be negative 1. And our degree looks like it is 6. Alright, so we're going to describe the end behavior and determine a possible degree of the polynomial function. Okay, so let's see what we can figure out. We can determine the end behaviors, but we can also we also know some things about the degree and the leading coefficient. All right, so they're in the same direction for this one. So we know that P is even. And because the right behavior is pointing up, we know that the K is positive. Now, for end behaviors, it looks like as we're going to the right, to infinity, the graph is pointing up. So as x approaches positive infinity, f of x approaches positive infinity as well. Now when we're going to the left, as x approaches negative infinity, what is happening to the graph? Let's see. Well, the arrow is pointing up. So it is approaching positive infinity as well. And remember what I told you guys before, that the end behaviors for even functions, or I'm sorry, even exponents, even degrees, they will point in the same direction. All right, so let's look at the next one. So both pointing up, so same direction. So again, your P is even. Your K, right behavior is pointing up, so K is also positive. And then end behavior, it looks like the same thing that we had over here. As x approaches infinity, f of x is going up, so it approaches infinity. As x is going to the left, as it approaches negative infinity, the graph is still going up to positive infinity. All right. So identify the end behavior of the polynomial. So describe the end behavior and determine the possible degree of the polynomial function. So just like we did on the last example. Pause the video and then come back and we will go over it. Alright, it looks like we're pointing down on both ends. And what that tells us is that our K is negative because the end behavior on the right is going down, but our degree, our exponent, is even because it's going in the same direction. Our end behaviors, as x approaches infinity, f of x approaches negative infinity because it's going down. As x approaches negative infinity, as it goes to the left, the graph is still going down, so f of x approaches negative infinity as well. Okay, so given the function expression, given the function, express the function as a polynomial in general form and determine the leading term, degree, and end behavior. So what you want to do here is you want to simplify. So we have f of x is equal to negative 2x squared. I would multiply this first x minus 2 times x plus 3 first. So I would get, I'm just going to go over here to the side for those that need it. So x times x would be x squared. X times 3 would be 3x. Negative 2 times x is negative 2x. Negative 2 times 3 is negative 6. So we would get x squared plus x minus 6. Okay, from here, we need to distribute the 2x squared, negative 2x squared rather, to each term. And I get f of x is equal to negative 2x to the fourth minus 2x to the third plus 12x. So we are looking for the leading term, the degree, and the end behavior. All right, so the leading term is negative 2x to the fourth. The degree is the highest exponent, which is 4. It's degree 4. And so then end behavior. Well, let's look at our A or K, whichever one you want to call it. That's negative 2. It's negative. That means the right behavior is pointing down, and because the P is 4, that means that the left behavior is pointing in the same direction. So it's going to look something like, as far as the end behaviors go, it's going to look something like this. There could be some curves along the middle, but the ends would look like that. So as x approaches infinity, or as x approaches negative infinity, either way, f of x is going to approach negative infinity because it's pointing down. Alright, so your turn. You guys try it. Given the function, 0.2 times x minus 2 times x plus 1 times x minus 5, express the function as a polynomial in general form and determine the leading term, degree, and end behavior of the function. So pause the video and then unpause when you're ready to go over it. Alright, so first we need to put it in general form. So I have f of x is equal to 0.2 times x minus 2 times x plus 1 times x minus 5. And it's up to you the order you want to go in, but it's multiplication, so you can multiply in any order. So I'm just going to start at the end here. I'm going to do x plus 1 times x minus 5. And I'm going to end up with x squared minus 4x minus 5. Alright, so now I'm going to multiply the x minus 2 times the x squared minus 4x minus 5. So to do that, I'm going to multiply the x times the x squared and get x to the third. X times negative 4x is negative 4x squared. X times negative 5 is negative 5x. Then I'm going to distribute the negative 2. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 4 is positive 8x. Negative 2 times negative 5 is positive 10. And 0.2 is still outside of that. On the inside, we can add like terms. So x to the third. Negative 4x squared minus 2x squared is negative 6x squared. Negative 5x plus 8x is positive 3x. And then bring down your 10. And then we're going to multiply everything times 0.2. So first we have 0.2 times x to the third. Then 0.2 times 6 is 1.2 x squared. Then 3 times 0.2 is 0.6x plus 10 times 0.2, and I get 2. So that is general form. This is f of x equals. And then the, let's see, we need the leading term, which is 0.2 x to the third. We need the degree, which is 3, and we need our end behavior. So let's see, the degree is 3. So that means that the end behavior is opposite directions, and we have a positive 0.2, so it's positive, so the right behavior is pointing up. So end behaviors look something like this. I don't know what's going on in the middle, but I do know what happens on either side. So it looks like as x approaches infinity, f of x approaches infinity, it's going up. And then as x approaches negative infinity, it looks like f of x is going down, so it approaches negative infinity. All right. Okay, so I'm going to stop the video here with part 2, and we will pick up with part 3, where we will talk about local behaviors of polynomial functions.